So last time we talked about this operator and the analogy between vector space and Hilbert space in quantum mechanics. All these quantum states and wave functions can be represented by a row of column matrices, and operator in quantum mechanics can also be represented by a matrix of n by n. We continue talking about this Hermitian operator that we introduced last time. The definition of a Hermitian operator is that the expression value of an operator A is the same as the complex conjugate of that expression value. As a result, expression value of the Hermitian operator is always real. You put it in a more mathematical abstract form. This is to say that A plays the same role as A dagger, but we will see an example which seems to violate this relation that A is same as A dagger for this Hermitian operator. But the most fundamental relation to define this Hermitian operator is this one. This is the more basic definition. And the consequence of this Hermitian operator is the following, that if you calculate any expression value of A operator, since A plays the same role as A dagger, so you simply just replace A dagger in the middle of this calculation of the integral. And the reason is that this and A dagger could be interchanged if you follow this Hermitian conjugate of this matrix. Another consequence of the Hermitian operator is that for non-degenerate two eigenstates of this Hermitian operator A, these two states are orthogonal to each other. U1 and U2 are the two non-degenerate eigenstates of Hermitian operator A. As a result, the overlap integral between U1 and U2 vanishes. So different eigenfunctions are orthogonal. So we will come back to this just a moment. Here is a very important kind of a clarification of this definition of Hermitian operator, is the example from this momentum operator we discussed many times. So remember, this momentum operator is defined as this h bar over I and this partial derivative of the wave function with respect to x. And we will show that this momentum operator is a Hermitian operator, meaning the expression value of this momentum operator is the same as the star of this p expression value, meaning this momentum average or this expression value of momentum operator is the same as the expression value of a p dagger. However, naively, you will find very confusing result, because if you naively simply just take the Hermitian conjugate of this p operator, and you will find that this is minus h bar over I d by dx, which is not the same as p, because p is plus h bar over I and p dagger is minus h bar over I. How can I say that p is the same as p dagger? P is not the same as p dagger. However, we will show that this expression value of the p is the same as expression value of the p dagger. So this is what I mentioned previously, that for this Hermitian operator, you have to understand their Hermitian properties only through this expression value. In many cases, you can. Okay, you can simply just take the Hermitian conjugate of the matrix, you find that they are the same, and you say this is the Hermitian operator, but the moment operator is an exception. This example tells us that you really need to stick to this most fundamental definition of the Hermitian operator, meaning the expression value of the operator is the same as the star of the same expression value. So naively, you would think that p dagger is not the same to p because there's a minus sign difference, but this is wrong. This is wrong. This interpretation and understanding is wrong. The way that you show this momentum operator is indeed a Hermitian operator has to follow this, again, this expression value that we define here. Okay, so the expression value of the momentum operator sandwiched in between any two quantum states or Schrödinger wave functions is given by this integral. This is the formal definition of expression value. So now you start from here, you actually can play this mathematical trick by this partial integration or integration by parts, you could use your knowledge in calculus and transform and rewrite this integral in terms of the boundary value, and plus another integration, which is the other way around, where this derivatives actually apply to f or f star. So this is integration by parts. Okay, so we know very well that at the boundaries all the wave function vanish. Okay, so plus minus infinity is this boundary value, this vanishes. You have the remaining integral. But if you rewrite the remaining integral in a standard form, where this moment operator is acting on this f, you take the star of this bracket, and then you could, by definition, you could simply just rewrite this pf star as f star p dagger. So the last line is precisely the expression value of a p dagger, because p dagger is in the middle between f star and g. Now you complete a circle that you show that this p expression value is the same as p dagger expression value. This is a very important lesson. You cannot simply just take the complex conjugate of the p operator and say that they are not the same. No, you are wrong. You need to take the expression value and show that both expression value give you the same value. In that sense, we say that p plays the same role as p dagger. So even though p is not the same as p dagger, p operator, if you superficially just take the Hermitian conjugate, is minus p dagger. But this interpretation is wrong. We need to really interpret this as the expression value of the p is the same as p dagger expression value. In this sense, we say that this p momentum operator is Hermitian. But in most cases, especially when this operator A is the matrix of n by n size, if you take the Hermitian conjugate of A operator and you find that this is the same as A, in most cases this is fine. But if this is the case, then of course if you take the expression value of this A and A dagger, you of course find that they are the same. However, for the momentum operator, you cannot do this. You have to stick to this expression value. So this is the very important remark. So let's just continue. Let's define the Hermitian operator of a product of operators. If you make a product between these two operators, what does it mean? So this goes back to the definition of the quantum mechanical measurement that we mentioned many, many times. So if I write this operator product like this, A times B, what I mean is this one. What I really mean is that I take two measurements. So I measure this psi wave functions by B initially, then by A later. So this means that I take two measurements. One is done by applying B onto the psi. This is the first measurement or operation that I take. You know very well that when I take the measurement of some quantum mechanical states by an operator, and the result is still a quantum states. This is another state which I call this phi. Then I should take the second measurement, and this leads to, say, another state called Xi. This is the order of this measurement. So the first operation, is the same as the first measurement, is done by applying B onto psi, and you get some other states, which I call phi, and then you apply A operator to phi to perform the second operation or the second measurement. We will just discuss this interchange of this ordering between A and B and A. So this is, say, the first set of successive measurements, which is done first by B and then by A later. but we can think about the reverse order, which is done first by applying A onto psi and then later by B. So the second process is done by measuring this psi by A first, then by B. In classical mechanics, it doesn't matter whether you measure the classical, say, particles first by B, later by A, or first by A and later by B. Okay, but quantum mechanically, it matters. The order matters. So this means that it not necessarily be the case that AB acting on psi is the same as BA acting on the same state. It's not always true. Okay. In general, it is not true. We will see an example. You already learned this example, X and P. When AB applying to psi is not the same as BA acting on the same state, we said A and B are not commuting. But if they are the same, we said A and B are commuting operators. Okay, so this is very important concept. Depending on the nature of A and B, so if AB is the same as BA by acting on this quantum state, and we said A and B are commuting operators, or A and B operators are commuting, or A and B commute. If not, then we said A and B operators do not commute. So whether any two operators commute or do not commute make a huge difference. So we will make remark and consequence of this commutation relations between any two operators. So let's take a short break. When we come back, we will continue defining this Hermitian conjugate operator of the operator product A and B. You will see later that commutation relation between any two quantum mechanical operators is really tied to the Heisenberg uncertainty relation. In a more mathematical formulation of this Heisenberg uncertainty relation is that any two measurements that are done by two operators, if they commute, then we could simultaneously determine these two measurements in 100% accuracy. But if they do not commute, then we should follow the Heisenberg uncertainty relations. They do have the uncertainty relations, and this uncertainty, this h bar over 2, is actually coming as a result of this commutator between A and B. Commutator is really the key to understand this Heisenberg uncertainty relation. Okay, so we will come back to this in just a moment. So let's just continue to define the Decker operator for a product of two operators, A and B. So suppose that A and B are the two operators that act on this phi wave function phi. We would like to define the star of this operation, a Hermitian conjugate of this A-B operation. For this order, we know very well that since A and B are two operators, so the product of these two operators is still a quantum mechanical operator. These A-B operators are quantum mechanical operators. If I write this operation like this, effectively, this could be considered as another operator, C, which is simply just defined by this A and B. And likewise, I can make a product between B and A, and I can define this as another operator D. C is not necessarily plays the same role as D, because as I mentioned, AB acting on the same state is not necessarily the same as BA acting on the same state. But in any case, AB plays the same role as some quantum mechanical operator C. So it's BA. Okay? So if I consider this AB operator is just some single quantum mechanical operator C, then I can simply just follow definition of the single Hermitian conjugate of the single operator. This is the standard definition of a single operator and its dagger. But now remember, the C is not made of the single operation, but made of two operations like this. But then if you really want to separate this AB dagger into A dagger and B dagger, you'll show that this is the correct result. So you need to really switch the order between A and B and then put the dagger on both operators. In other words, it's very important to understand that this AB dagger is not necessarily the same as A dagger, B dagger, but it's really B dagger, A dagger. When you take this dagger of the product of the two operators, you need to switch the order between these two and then put the dagger. As I mentioned, the order matters. But this AB dagger, in some cases, can be the same as A dagger, B dagger. But this circumstances is that when A and B commute. So when A and B commute, you can put whatever order you like. But when they do not commute, you should really follow this correct order. So let's just prove this correct order. Assume that when B acting on this phi, I get some other states, which I call this chi of x. Whereas as I mentioned, if you understand all this quantum mechanical operation as matrix product, and you know very well that n by n matrix acting on n by 1, you'll get another matrix of n by 1. In other words, when this B operator acts on this phi state, and it will give you another state, which is not the same as phi. Not necessarily the same as phi, and we call this chi of x, which is again another quantum mechanical state or wave function. We rewrite this operation in terms of this chi states or wave function. So now we actually plug in this chi that we assume right here. We get to this integral. We know very well, since this is just a one operator remaining, and we simply just follow the definition of this A chi start. We know that we need to switch the order between chi and A, and we put start or dagger on these two states objects. So this is what chi star A dagger and psi, right? So now we simply just restored what it means when we define this chi states, right? So the chi, the wave function chi, is given by B acting on the phi. B phi star and A dagger psi. Because chi is simply just B acting on phi. So now here comes the same stuff. So we simply just follow this, the star of the combined object or matrices, and we should interchange the order between B and phi, and we put star or dagger. Check. So again, as I mentioned, the correct dagger of AB operators is actually B dagger, A dagger. It's not A dagger, B dagger. So here's a very good lesson. If you really want to take the dagger, any product of operators or matrices, you should really interchange the order and then put a dagger on all operators. We can generalize this definition of the dagger on the product of many operators. Suppose we have a product made of A, B, C up to Z, that many operators, and I put the dagger on this bracket of the product operator. Then the correct way of separating this bracket is to actually reverse the order of this product and then put the dagger on all operators. we can actually construct the Hermitian operator from any operators. If there is any operator Q, may not be Hermitian, but I can construct, based on this Q and Q dagger, the Hermitian operator. We can show that Q plus Q dagger and I times Q minus Q dagger, or Q times Q dagger, are all Hermitian. Because to show this is a Hermitian is very easy. You simply just consider this, the whole thing, as a single operator. You take a dagger of that, the whole thing. If I take a dagger of this Q plus Q dagger as a whole, then I should simply just separate these two operators because there's a summation here in the middle. By the property of the linear operator, you can simply just separate these two. For the first one, you get Q dagger. If I put a dagger on this first one, the second one is actually Q dagger dagger. So what is Q dagger dagger? It's like a double negative. It's actually positive, right? If you take the double Hermitian operation, you go back to the same operator because, again, use your knowledge of your complex number. If you put the start on A minus IB, you get A plus IB. But you put another start, which goes back to the original complex number. So likewise, the double dagger or double Hermitian is no Hermitian operation. So Q dagger dagger is the same as Q. When you take the Hermitian on this bracket, you get Q dagger plus Q, but Q dagger plus Q is the same as Q plus Q dagger by the linear operator, the properties of linear operators, so they are the same. So likewise, you could show the following two operators, the combination of this Q and Q dagger, give you a same Hermitian properties. For example, if I take this dagger, what does it give us? When you take the dagger of I, you get minus I, and Q is Q dagger, and Q dagger dagger is Q, right? You simply just put minus sign in the bracket, you get what? Minus Q dagger plus Q times I. Minus Q dagger plus Q is the same as Q minus Q dagger. So they are the same. So again, so you put a dagger, you get what? Q dagger, Q dagger dagger, and Q dagger. Because you need to switch the order between Q and Q dagger when you take the dagger on the whole thing. On the left, you should put this Q dagger and another dagger. On the right, it's just a single dagger. So this is the same as Q dagger. You can imagine that you have infinite number of ways to construct a Hermitian operator made of any operators. So let's take a short break. When we come back, we'll make a final remark concerning the commutator of any two operators. So far, it's just a linear algebra and matrix product. Okay, so this is all you need to know. Okay.
老师，不好意思，刚刚 I 乘以 Q 减 Q dagger 那边那一条式，可以再解释一下吗
Okay. To show this is Hermitian operator, we need to take the dagger of the whole thing. You simply just use the linear algebra, help you. So I can separate this as IQ minus IQ dagger, and I put dagger. Yes? So because this is just plus minus sign, I can simply just separate this by the linear properties of these operators. So this is the same as IQ dagger minus IQ dagger. Agree?
Agree.
Okay. And you simply just take this dagger for these two objects. One is this imaginary number I and Q dagger. And the second term is what? This is minus I Q dagger. Yes? As I mentioned, this double dagger is no dagger. So, and minus 1 is plus. This is what IQ minus IQ dagger. The same thing. Everyone understand this? This is a very simple algebra. So let's come to the final remark, which is very important, which says that even though these A and B operators are Hermitian operators, are the product of these two operators, Hermitian operators, may not necessarily be Hermitian operators. Say that clearly if A and B operators are Hermitian, the A-B product may not be Hermitian. If you know that A and B operators are Hermitian operators on their own, and you make a product between A and B, and you may guess that this operator AB is also Hermitian because A is Hermitian and B is Hermitian. Well, but the truth is that no, they are not necessarily Hermitian operator. So let's just prove this statement. Suppose A and B are both Hermitian operators. I take a product of A and B and I put a dagger on the bracket for the whole thing. Follow this definition of dagger of a product of operators. You get B dagger, A dagger. But you know that B dagger is the same as B and A dagger is the same as A if you BA. But in order to show that this AB as a product is Hermitian, you need to show that the dagger of AB is the same as AB. So if this product operator is Hermitian, then AB dagger will be the same as AB. But is that so? No. Because if you take the dagger of AB, you get BA is not AB that you wanted. But they differ by a commutator. Okay, because BA could be rewritten in terms of AB minus AB plus BA. You simply just add and subtract this operator product AB and to actually form this bracket AB minus BA, and this is defined in quantum mechanics a commutator between A and B operators. So this is really the key point. So the AB dagger is what? Is AB minus the commutator between A and B. So as I mentioned, any two quantum mechanical operators may or may not commute. If A and B commute, and fine, and the product of AB also commute. The product of AB is again a Hermitian operator. But if AB do not commute, then this AB product operator is not Hermitian. So let me just write in words. If AB commute, then AB operator as a product is Hermitian. If not, then they are not Hermitian. Okay, so this equation tells us these two statements that whether AB product can be Hermitian operator or not, depending on whether they commute or not. So if the AB commutes, this commutator vanishes, then they do form a Hermitian. If not, then it's not Hermitian. Everyone understand this? As a result, whether these two operators commute or not really matters. So let's just remind you a very well-known example of the non-commuting operators, X and P. Remember that. Anyone tell me what this is? XP is what? IH bar. Yes? If you go back to your note or textbooks, you'll find that this is the first non-commuting sets of operators that we encountered so far. The X operators and momentum operators, they do not commute. The commutator between X and P is given by a number IH bar, which means that if you want to measure any wave function by successively applying these two operators in different orders, you may get different results. You should get different results. It's not the same as. And this has a huge consequence of this uncertainty or error bar when you take the measurement of any quantum states by applying x and p. So when you measure the momentum on any states, you actually measure some kind of a momentum eigenvalue, the eigenvalue of the momentum operator. When you take the measurement of the position, you apply the x operator. And this two operation tells you that you first measure this momentum on some quantum particles and later measure the position. And this result is not the same as you do things in the reverse order, saying that you first measure the position and you measure the momentum. This really tells us that there is a uncertainty relation right here. So let me just tell you formally this relation between the commutator, the uncertainty. If there is any two operators, A and B, they do not commute. And when these two operators do not commute, there is a Heisenberg relations, uncertainty relations. You could imagine that I can define my error bar when I take the measurement for A and B, and I make a product between these two error bars, delta A and delta B, where delta A and delta B are defined here, just a standard deviation. Delta A and delta B are simply just error bar or standard deviation. When you take the measurement, there must be an error bar, and the error bar is defined by the standard deviation that you know from your mathematics, statistical mechanics. Delta A is the square root of this A square expectation value minus square of the expectation value of A. And it says that we will prove this theorem later, but the statement is that the error bar for A, delta A times the error bar for B is greater or equal to, is greater than or equal to this quantity on the right hand side, which is 1/4 times a square of this I times this commutator A and B. So let's just put this in a physical context, which is x and p. Suppose A represents this x operator and B represents the momentum operators. Delta A is actually delta x, delta B is delta p. So the theorem says that delta x times delta p is greater than or equal to this 1/4 of this square of the thing. So this is what I times x and p is what commutator is I h bar. So it's I h bar. Sorry, this is square. Square, the right hand side is given by what? 1/4 times h bar square. You take the square root of this inequality and you get exactly this Heisenberg uncertainty relation. Okay, so this is a very important inequality in quantum mechanics, is the origin of the Heisenberg uncertainty relation, which means that if you have non-commuting operators A and B, as a result, there is a Heisenberg uncertainty relation associated with that measurements A and B. The relation is precisely the same as the one that we are familiar with, delta x, delta p, products greater than or equal to h bar over 2. Here is the relation, formal relation between the Heisenberg uncertainty principle, the commutator between two operators. If we have two commuting operators, then there is no Heisenberg uncertainty relation. Why? If A and B commute, then you can show that delta A squared times delta B squared is actually greater than or equal to 1/4 of what? Since A and B commute, this commutator vanishes. So the right-hand side of the inequality exactly becomes 0, which means that delta A times delta B is actually 0. And what does it mean? If the product of two error bar can be 0, which means that both delta A and delta B can be 0 at the same time. Right? So if I put this 0 here for delta A and 0 for delta B, and 0 times 0 is again 0. So we satisfy this so-called Heisenberg uncertainty relation, but there is no uncertainty because delta A is 0 and delta B is also 0. So you can simultaneously determine the A measurement and the B measurement. And there's no such uncertainty relation between A and B. And this is because, precisely as I mentioned, the A and B operators commute. So in other words, the reason why we have such a Heisenberg uncertainty relations for X and P is precisely because X and P do not commute. If the two operators commute, then they do not have uncertainty anymore. You can measure these two quantities in 100% accuracy at the same time. There's no problem. And indeed, we will have such examples later, but here I'm just telling you this very deep connection between the Heisenberg uncertainty relation, commutation relation between operators. Of course, we will prove this officially later, but we should emphasize the physical interpretation and understanding of quantum mechanics regarding the measurement, the error bars, the uncertainty relations. They all boil down to this commutator relation or commutation relation between any two operators. So I guess that's a very important message that you need to understand today. So let's take a short break. When we come back, let's continue, elaborate this very important ideas of commutation relations. In particular, we will show that if two operators commute and we can find a simultaneous eigenstate of these two operators, this is precisely what I mean by saying that you can measure these two quantities at the same time in 100% accuracy. And because we could show that there exists a simultaneous eigenstate. The concept of simultaneous eigenstate is really, really important because it's tied to the commutation relations between any two operators. If two operators commute, then we could construct a simultaneous eigenstate, which is the eigenstate of A and B at the same time, which is the eigenstate of A and B at the same time. So when the particle is in the simultaneous eigenstate of A and B, you could for sure measure these two quantities 100% accuracy because these two measurements are taken when the particle is in this simultaneous eigenstate. So when the particle is the eigenstate, you cannot change this fact because once the particle stays in the eigenstate, it will stay there forever. Remember that. If we can construct and show there is a simultaneous eigenstate of A and B, when we take the measurement, this particle really sit there, which is the same eigenstates of A and B. And for sure, we can have 100% accuracy when we perform such a measurement. All these concepts are connected very tightly. It is very important that you link all these relations and concepts in quantum mechanics. Commutation relations, Heisenberg uncertainty relations, and simultaneous eigenstate, error bars, and standard deviation, and Hermitian operators, and so on. Let's take a short break. When we come back, we will illustrate this idea of simultaneous eigenstate. Up to now, I think we already depart or deviate from this modern physics or quantum physics. We are inside of the quantum mechanics. In quantum mechanical language, we should use that terms to understand this important consequence in the quantum world. From now on, you should think of all the quantum mechanical problems in terms of all these important concepts. When you look at any two operators, the first thing that you need to ask is, do they commute? If they commute, then there's a consequence of that. If they do not commute, there's another consequence of that. Also, you should ask whether there's a degeneracy or simultaneous eigenstate, which are also related to this commutation relation. And also, you should ask whether they are Hermitian operators, things like that. But the most fundamental relation in quantum mechanics is the commutation relation. From now on, we'll actually discuss and study the commutation relations all the time. Now, some people say that quantum mechanics is about commutation relations. I think it's about right. What you should think and what you should study is what? Commutation relations and commutation relations and commutation relations. I should emphasize this concept 3 times because this is the key, it's the heart of the quantum mechanics. It's the commutation relations. So let's just link the degeneracy, simultaneous eigenstates, and the commutation relations. We should discuss the relation between these commuting operators between A and B and the simultaneous eigenstates of A and B. So let's just prove that simultaneous eigenstates of A and B really goes side by side with their vanishing commutator. Meaning this is the statement on both sides. Okay, meaning this is a necessary and sufficient condition. Meaning we can go from the left to the right or reverse from the right to the left by saying that if we have a simultaneous eigenstate of A and B, then A and B must commute. Or if A and B commute, then we must be able to find a simultaneous eigenstate of A and B. This is both necessary and sufficient condition. In other words, you could just consider them as an equivalent statement. So if A and B commute, then we find the simultaneous eigenstate. If there is simultaneous eigenstates of A and B, and it must commute. So let's just prove this statement. So let us define what I meant by the simultaneous eigenstate of A and B in a more mathematical way. Suppose there exists such a state, which is UAB as a function x, which is some kind of a eigenfunction, a wave function. So this wave function is a eigenfunction of an A operator. When you apply this eigenvalue equations by applying A onto this UAB, you get eigenvalue A times this eigenfunction UAB. But the UAB is not only the eigenfunction of A, but it's also eigenfunction of B. Just a different eigenvalue when you do the same measurement or this operation. When B acts on the UAB, this gives you an eigenvalue B times UAB. Both equations are satisfied. So UAB satisfy the eigenvalue equation for A and also for B, okay, with a different eigenvalue. And this is the definition of a simultaneous eigenstate. Suppose we have such a state, which we do have. There are millions of examples in quantum mechanics that you could have such examples that some eigenfunctions can be eigenstates of 2 operators. So if this is the case, then we can show that these 2 operators do commute, which means that we go from the left to the right. Let's just prove that if we found such a simultaneous eigenstates of A and B, then they must commute. Okay, so let's prove this. It's very easy, just one line. Because I mentioned, let's just write the definition of a simultaneous eigenstate. So again, to show this commutation relation, you must perform two measurements of the different order, AB and BA. You first do this AB, have two measurements on this UAB. You first use the B operator to act down this UAB state, because this is an eigenstate. UAB is eigenstate of B with the eigenvalue B, so you write down the eigenvalue B. Since this is just a number, so you can actually move it to the anywhere you like. So I move it to the left, so then you're left with this second operation, A acting on UAB. Following this similar eigenvalue equation, you get the eigenvalue A right there times UAB, so you get altogether two eigenvalues, A and B, multiplied together. So this is the first operation. So you could do the same thing for the opposite operation, where you apply BA acting on the UAB, so you get the same thing. So it's BA UAB, which is AB UAB, which is AB UAB. Okay, so you get the same thing, so of course they commute. So you simply just subtract one from another. AB minus BA acting on the UAB. You get little ab minus little ab times UAB, which is 0, because little a and little b are simply eigenvalues. They are just numbers. Little a times little b is the same as little b times little a, so ab minus ba is 0. Check. ab as the operator minus ba acting on this simultaneous eigenstate vanishes, which means that this must hold for any arbitrary, say, UAB. As a result, this commutator vanishes, must vanish. Okay, so we prove from the left to the right. So from now on, you should remember that if we have such a simultaneous eigenstates of A and B, and these two operators must commute. Well, of course, you could generalize this proof by constructing any arbitrary wave functions. So let me write it here. So suppose psi is the arbitrary wave function, which is linear combinations of all eigenstates. You could show that again, so AB acting on psi is exactly the same as BA acting on psi. So again, so it doesn't matter which wave function or which eigenfunction that you start with. It's always the case. So let's just discuss the other way around. When we have such a simultaneous vanishing of a commutator between A and B, whether we can find a simultaneous eigenstate of A and B. There's a question mark because it depends on whether there's a degeneracy or not. If there's a degeneracy. For degenerate states, we should actually discuss separately. So let's just discuss first if there's no degeneracy. So remember, degeneracy means that you have two different eigenstates of the Hamiltonian, but the eigenenergy are the same. Suppose I have, let me just define this degeneracy one more time. Suppose you have these two states. The white and orange states are different states. However, if you applied this operator on this u, you get some value, eigenvalue. You also do the same thing for v, you get the same eigenvalue. Would you call that we have the two degenerate states? Do not get confused between this simultaneous eigenstate and degeneracy. For simultaneous eigenstates, we say that it is the same state, which is the eigenstate of the A and B, but the eigenvalues are different. But for degeneracy, the U and V are different states. U and V are different states. of the same operator A with the same eigenvalue. These are two different situations. Don't get confused. Suppose there's no degeneracy, meaning we don't have such a degenerate situation like this, then we could very easily prove that when the two operators A and B commute, do find a simultaneous eigenstate of A and B. So let's just prove this. Again, we should take advantage of this different measurement. One is AB, another is BA. Okay, so let's start with this AB acting on the U, where U is some function, it's eigenfunction. So let's just perform the first manipulation. First, we know that A and B commute. We simply just reverse switch order between A and B. AB acting on the U is the same as BA acting on the U. Next, we simply just apply the eigenvalue equation for A. For that reason, I need to consider eigenfunction of A operators. Suppose U is UA, which is the eigenfunction of an A operator, and then I can simply just apply this eigenvalue equation for A acting on UA, which giving the eigenvalue little a, and then another operation which is yet to be done. However, let's just look at the different side of the same equation. Suppose I simply just consider this rest circle. The rest circle represents some quantum state, which I don't know, because this B acting on UA is some other quantum states and can be represented by some wave function, which may be any wave function. But if you look at this red circle and some unknown wave function psi, suppose this is, say, a phi of psi, so this is a phi of x, I could simply just rewrite this eigenvalue equation for phi of x, A acting on phi, going to be little a times phi, which says that this phi of x is also the eigenstate of A. But what is phi of x? Phi of x is nothing but this B acting on U, meaning that when B acts on U or UA, this is also the eigenfunction of A. So I can simply rewrite this statement in a mathematical form, which says B acting on UA is actually eigenfunction of A, which is proportional to UA, with a different prefactor or proportionality, which I call this B, little b times UA. Because B acting on UA is the eigenfunction of A operators. What is the eigenfunction of A operator? Well, it's UA. But any function made of UA by a prefactor, which I call this little b here, is also an eigenfunction of A, right? Because when A acting on this B times UA is actually what? AB times UA. Any arbitrary prefactor B multiply UA is also an eigenfunction of A. Okay, so this statement tells us that B acting on UA is an eigenfunction of A, but maybe with a different prefactor, which I call little b here. But at the same time, remember, A acting on UA is eigenvalue little a times UA. So you combine these two statements. This is precisely what I meant by simultaneous eigenstate, because this UA is an eigenfunction of A operators, and it is also the eigenfunction of B operators with eigenvalue B. UA is a simultaneous eigenstate of A and B operators. Please pay attention to all these eigenvalue equations. Again, this basic principle of quantum mechanics, when we perform this measurement, or if we really act any quantum states by operators, remember they are simply just matrices. So if we take a measurement like B acting on U, the result is some other state. So let me just write down some key concept that you should remember. A acting on any wave function is actually any other wave function. You apply the operators onto any quantum states, and you end up with another quantum state. This comes naturally if you consider this operation as the matrix product. As I mentioned many times, this operation is nothing but the product between n by n and n by 1 matrices. The resulting matrix is, again, n by 1. So any matrix which is n by 1 could be understood in terms of some quantum state. When operator acting on some quantum state, you end up with another quantum state. Likewise, if you apply successively two operators, A and B, on any quantum states, you end up in doing the same thing if you consider a single quantum operator, C, which acts on the same quantum state. So two operators can be represented by some other single quantum operator. So this concept is really useful and necessary when you try to understand all these different concepts and statements. It is extremely useful, especially in terms of a matrix product, column and row matrices for quantum states or wave functions. So later we will rewrite our Schrödinger pictures in terms of the Dirac matrices. Things will become later. But here, remember, when we take the measurement, we apply an operator onto any quantum states, and we get another quantum state. Two operations in quantum mechanics can be a single third quantum operator. Multiplication of different quantum mechanical operators can be constructed or considered as a single different quantum mechanical operators, which says that you multiply this A and B matrices, you get a different matrix of the same size, n by n, which means that you could represent this A and B product in terms of a single operator, C, in the matrix form. Okay, so I guess that's enough for today. Let me summarize. We introduced the concept of Hermitian operators, the commutators between two operators, the relation between the commutation relations, the Heisenberg uncertainty principles, and also the connection between the simultaneous eigenstate, the vanish of commutator. So all these concepts are very important. I suppose that many of you have not studied this. This is the heart of quantum mechanics. Okay, so please read our textbooks. Okay, so see you tomorrow.